Unfortunately, it got erased somewhere as a result by Schenfeld and Van Hendel, which says that paraphrase it, Alexandrov-Fenchel equality cases can be, what did you say, completely characterized. Characterized for KL, I think you use notation C1 up to Cn minus 2, and those are equal. Equal polygons.
No, not equal.
Not necessarily equal, but the polygons. Okay, so I'm going to give you a somewhat counterintuitive theorem, which says that so this is a result by Swihong Chan and myself. Wait, this is, well, it's also 23, but it was this one written 23. This was published in 23. So it goes sort of the same way. Equality cases cannot, and then so cannot be completely corrected. Now, when you're looking at this, you're probably asking questions, right? So hold on with the question. So the real issue is what does that mean? What does characterized mean? And since Ramon never stated his theorem, I cannot point to and say, well, that's not right. That is not what one should think of complete characterization, because he just said it can. Yeah, but what does it really mean? So, so essentially, their version of completely characterized is they're saying the geometric meaning is clear. And we're saying that combinatorial slash computational complexity meaning is not clear. So in fact, it's actually probably hard to characterize in lots of cases. In exactly the same setting as Ramon and Yair are doing it. Okay, so I'm obviously going to give you a little more details later, but so let me maybe make a plan for the talk. So here's a plan. It will take me a little bit of time to explain what I'm doing. So I'll start with why. And thankfully, Ramon already covered a lot of this. I'll just mention a little bit. Why is that important? Then I'm gonna answer, what does this all mean? What is the statement of the theorem? It will take me a while to get to that point. I'm gonna then explain as much as I can. How can one possibly prove what took some pains to explain? Okay, and then if there is time, really, why? So this is going to be completely different from that one. Okay, because this is the question, and the way to distinguish that this is why from the point of the area, and this is really why from the point of completely different area. And that's where we're going to go. Any questions before I start telling you some math?
Oh, it's all still about polytopes, right?
Yes. Yeah. I don't do any of the rest. Any other questions?
K and L are not polytopes.
Yes, they are. Everything is going to be polytope.
In fact, the Ramon's theorem, K and L are not polytopes.
Well, Ramon can do wonderful things. I cannot. In fact, I'm going to prove that one cannot. Okay. So, and then Ramon said, Alexandrov, so everything goes back to Minskovsky, but Alexandrov was himself very interested in inequality cases for Alexandrov-Fenchel inequality. And he said, this is my own translation from Russian to English, serious difficulties occur in determining the conditions for equality to hold in the general equality we just derived. So immediately after he stated Alexandrov-Fenchel inequality, what we call now Alexandrov-Fenchel inequality, he was really interested in having equality cases. Okay, and it's sort of continued for a long time, and in fact, it's a big tradition which has a reason why prove inequality cases for geometric inequalities or more general inequalities. I'll just give you a quote from Gardner that I like, that I sort of recently discovered. So this is sort of like a proof of importance by appeal to the authority. If inequalities are silver currency in mathematics, those that come along with precise equality conditions are gold. Equality conditions are treasure boxes containing valuable information. Okay. So,
sorry, who is that?
Gardner.
Martin Gardner?
No. Completely different Gardner. But still Gardner. This is from his survey on Minkowski inequalities, where he discusses a lot of equality cases which are relatively easy and various generalization of such. Okay. So Ramon mentioned quickly stability, and it's sort of worth elaboration a little bit about that. So let's see. If you have, it's easier to explain this already for the parametric inequality. Let's say you have a convex body. If you like, this can be a polygon, but you don't have to like that. And so we have a really interesting inequality that L square, let me write L of x. So this is a perimeter of the body, square greater or equal to 4 pi area. So that's my other parametric inequality. Now, what does stability mean? So from the equality condition point of view, equality conditions are questions: when is this equality? And we all know that. That happens for circles. But stability captures more than that. So let me just write it differently. 4 pi a is greater or equal. It's actually 4 pi times r minus r squared. So it turns out that you can give a lower bound on which is non-negative on the defect of the parametric inequality. This is something called Bonazon's inequality. And now, if you're paying attention, not asleep yet, you should be asking what is big R and what is little r. And let me see if I can try to draw that. So what one can do is that one can look at the circle that contains your convex body and a circle inside of it. So, so if you take the smallest r that contains your x and the largest little r of a circle that's inside your x, that's how this r and capital R and little r are defined. Okay. And in fact, Bonazon showed that you can make them concentric, so to have the same center. Okay. And that is quite surprising. But in particular, it shows that, yeah, if you want this to be 0, that means R is big R is equal to little r, which means that your convex body is a circle. Okay, and if you look at numerous analytic literature by especially famous in the works of Figali and his co-authors, you see a lot of results of similar type for Brun-Minkowski and other inequalities, but especially beautiful for Brun-Minkowski with different functions. So what they find is for the best function you can put on the right. We're fighting for we're asking whether there exists any function like this at all for the Alexandrov-Fenchel, because so Brun-Minkowski inequality it actually isn't. I won't even say it, but it's. I'm assuming you know that it's an easy consequence of the Alexandrov-Fenchel inequality. So for Brun-Minkowski, the equality conditions are quite easy. It's what Ramon calls the first translation expansion. And now stability comes from asking how similar two bodies to each other up to scaling and parallel translation. What happens when you don't exactly overlap? Now, so that's it. That's all I have to say about the first question. Can I move on? Okay. So maybe as a transition to why this stability is important is, well, not why it's important, but how is that related to equality cases? The typical logic, if you talk to people who actually work analysis, they're going to tell you that, well, we're really not interested in equalities where the equality cases cannot be characterized, because how else would you come up with a function like that? Okay, so that's how we're going to transition. Okay. So now I want to get back to, so this is, let's do this part 1, part 2. So the statement, so let KL, I'm going to use Q1 of the Qn minus 1 in our convex polytopes. And I'm going to slowly try to write the theorem. So this is theorem by Zwiefenkrantz and myself, where we're saying that equality cases of Alexandrov-Fenchel inequality are not in the polynomial hierarchy. I'm going to explain what I mean by all of this. Now, once you write a computer science result, you need to understand what I'm talking about. How are these polytopes defined? And there is an obvious answer for that. Every polytope is defined by some kind of set of inequalities. Okay. So this is a matrix. This is a vector. So we're considering all x in Rn, which satisfy the system of inequalities. Now, if you would want to have A and B to be rational, otherwise you cannot input that into a computer. Okay. In fact, we will make them in. So I'm going to make a definition. I'm going to say that P is a totally unimodular polytope if A is totally unimodular and B is just an integral vector. Now, what do I mean by totally unimodular? So I'm going to think of that as a matrix. All the entries are going to be in either 0. So everything here is going to be either 0 or plus minus 1. And in fact, all the minus, so all subdeterminants of this matrix are either 0 plus minus 1.
You mean the determinant?
So this is a rectangular matrix, and all the minors have to be either 0 plus minus 1 of all sizes.
Yeah, the determinant of all sub. Yeah.
Correct. Determinants of all submatrices. Now, once you add that implies that the polytope has integral vertices, in which case everything is super nice. Let me not constrain myself. I'm not in so equality cases of Alexandrov-Fenchel inequality for totally unimodular polytopes are not in polynomial hierarchy. So what we're doing is constraining the set of possible things that we're doing. Now, if you know anything about complexity, you know that there is no way it could possibly be proving such a result. First of all, one needs to understand that it isn't polynomial hierarchy, but that follows from our constraint to those particular nice polytope. That this lies in P space. Okay, and the reason why we cannot prove it is because complexity theory cannot prove anything unless Px collapses. Okay, and by collapses I mean collapses to the finite level. So Ps equal to sigma m. Let me not explain any of that. Okay, so basically it means that only finitely many quantifiers suffice to get any number of quantifiers. Okay. So is the statement vaguely clear? Any questions about this?
What do you mean by equality cases are not?
So that is that's a good question. So let me answer that. So we're looking at Alexandrov-Fenchel inequality and asking, is this an equality? That's what I mean.
So you're given.
So in fact, it's probably better to remove the word cases completely. Equality of the Alexandrov-Fenchel equality with a given input is not in the polynomial hierarchy. Now it's a decision problem. So the Alexandrov-Fenchel inequality, as you remember, I'm sort of assuming you remember from the previous talk. It basically looks like some mixed volume is going to equal to another mixed volume times another mixed volume. And we're asking if this inequality is an equality. Okay, go ahead.
But K and L are part of an input?
Say it again.
Are K and L parts of the input?
Yes.
Everything.
Everything here is part of it. The input is a collection of matrices A and vectors B.
And polytopes.
And polytopes, yes. It's not a three-dimensional result. No. Otherwise, this would be all easy.
I guess you need to require that A has polynomial size. It's not
No.
automatic in your.
No, it's the time is a function of the input.
Oh.
Yeah.
Okay.
Can we move on? Ask me questions, not each other.
Is the question
Hello?
question hard?
There is an echo. It's hard for me to.
Is it NP hard?
Well, that actually we don't know. I don't know where Gil is, so I'm gonna look at the camera. Not known. But mixed volume is actually sharply hard.
Wait, so it's worse than that, right? So even the volume is not
Sharply hard in general, yeah.
doesn't have a polynomial size.
But this is a decision problem, not a counting problem.
No, but you mentioned just the mixed volume computation, right?
Mixed volume
It's conceivable that you can decide it without doing the calculation. A priori, the fact that this is, Igor, don't be scared, it's nutty.
I know, but I should look at you there, but you're here. Go ahead.
I'm everywhere. No. The fact that the calculation is sharply hard doesn't mean that it's a priori, that the decision problem is difficult.
Thank you, Nati.
We all agree with that.
For example, decision problem whether the volume is greater or equal to 0 is very easy. Decision problem whether the volume is equal to 0 is also easy.
But what I was saying is that if a polytope is given indeed by linear inequalities, then the volume as the answer is not polynomially bounded in the input.
That is true, but that's why we restricted ourselves to this subset when it's not.
Mm-hmm.
So here everything is, because all the vertices are actually integral, everything is released. It isn't sharp PH. Go ahead.
What about membership to in NP?
It cannot be in NP because then this would mean that polynomial hierarchy collapses. Okay. So extremely unlikely. We cannot prove that PH is not equal to NP. I mean, if I could, I would probably win some prizes, but that's not happening anytime soon. Okay.
Igor, one more question. So is there anything about approximation in here? So for example, we had previously the bonus and inequality, which says how far the two sides end. Can you do something like to estimate the error, or that's hopeless?
That's not what we do. It's not just hopeless, it's orthogonal to anything I know.
Thank you.
Good. So now that we got through this the result, let me tell you how would one possibly prove that. And the answer is it's not easy. And what we really do, we really follow the same pattern that Ramon was telling you, but in reverse. Okay. So in fact, we don't particularly care about two polytopes. So what is the polytopes we're considering? So all these K, L, and Qi are going to be ordered polytopes. So Ramon didn't tell you what exactly ordered polytopes are, but it's actually not a difficult thing to define. Suppose we have a poset with an element. I'm gonna so here is going to be definition. I'm gonna need a couple of well, let me define order polytop. Order polytop corresponding to poset P is defined to have consist of let's see all let's say y. Oh, I don't know. Let's say x in Rn. Such that sorry, let me write it the way I like to write it. So I'm going to map from my poset x to 0, 1, such that such that f of little x less or equal than f of little y for every x less than y. Here we go. That's another polytop. And basically, the examples that we need for this to work are collections of K, L, and Qi corresponding to different posets. Okay. Now, what do we do next? Essentially, we're saying that equality conditions for the mixed volumes for those polytopes are hard to decide. Now, how? So let me actually tell you what is the volume. So it's sort of observation by Stanley that volume of the order polytop is equal to 1 over n factorial, and then number of linear extensions of a poset P, where linear extension is a map from x into numbers from 1 up to n, such that f of same conditions here. F of x is less of f of y for all x less than y.
Has to be a bijection, right? Otherwise,
Yes,
it would not
it has to be a bijection. That is correct. So we're looking at bijections from the ground set of a poset into numbers from 1 to n, which are increasing, which are order preserving. So with respect to the order, they're increasing. And now when you do that, suddenly you get an excess. You can translate your inequality into poset terminology. So let me state what it becomes in the cases, and this is what Ramon referred as generalized Stanley inequality. I'm going to use a slightly different notation. So is x less. I'm going to fix element x, element z1 up to zk. I'm going to take number a, number c1 up to ck. So these are in x, and these are, well, let me write some 1 up to n. And I'm going to define dc of pxa to be number of f linear expansions of a poset such that f of x equal to a, that's a special element, and zi equal to ci. So n is a number of certain linear extensions with fixed few values of elements. Okay, and following the same proof as Ramon explained, Stanley in 81 showed that n zc of pxa is log concave, which means that this number is greater than the same number pxa plus 1 times n zc pxa minus 1. So that is inequality. Okay, so this inequality is a special case of the Alexandrov-Fenchel inequality. It follows immediately from there. Okay, so what we're really saying, from a combinatorial point of view, what we're saying is the following. So here is the theorem. For all k greater or equal to 2, deciding equality of, let's call this inequality Stanley. Deciding equality of the Stanley inequality is not an pH unless pH collapses. Okay, and now I transport the problem from geometry, removed all geometry whatsoever. Now that's a combinatorial result. Okay, the question is, how would you even approach to do that? And that is difficult. Let me see how much time do I have. I don't actually know.
10 minutes.
Okay, so so you know how all computational complexity results are proved. What you do is you take a giant number of cases that you want to consider, find a very small subset, look at this subset with a magnifying glass, and you use it. So you reduce it to another problem. Then you take a very small subset there, look at it with a magnifying glass, you get it there, and you proceed to do that several times. Okay? So just like every result in computational complexity, we have a chain of reductions, and the very first reduction I'm going to explain, and maybe the very last one. So what one can do is consider flatness problem. And that is very, very similar to what Ramon was saying. At the end, when you have equality conditions for poset, turns out to become what he calls a geometric progression, just very short one. Okay. And now, so here is a question. So suppose you have NZC of PXA. Is that equal to NZC of PXA plus 1? That looks like a similar type of question, a simple type of question, right? You remember in the graphs that he was drawing, he had it sort of went flat for a while, then went up, then went flat, then went down, went here. So we're asking, do we get equality of the two consecutive ones? And so the way we prove that this is not in pH, by proving that this is not in pH in exactly the same sense. Okay? Is that not clear? Now, that already sort of has profound implications in the sense that, well, I don't know, profound, but sort of maybe slightly unusual. So what we're saying is that the picture could be like that. It could be that there exists unique maximum, or it could be there are multiple maximum. Okay? Even that cannot be decided in the polynomial hierarchy. Okay? And so let me write a sort of I suppose final reduction. So you go from so in general you go from Alexandrov-Fenchel to Stanley, from Stanley to flatness, and then there's a long story. But at the end of the day, you're asking the following question. So I'm going to define. So I'm going to define a relative number of linear extensions, rho of Px, to be number of linear extensions of P divided by number of linear extensions of P minus X, where X is some element in my ground set. Okay. So the very final question is whether rho of Px is equal to A over B. So in a similar way, this is sort of after massaging this flatness for a while, we get down to this problem of decision whether this ratio is actually whatever you think it should be. And that turns out to be not in the polynomial hierarchy.
What are A and B?
Given integers.
Any.
Yeah, I give you two integers, 17, 25, whatever it is. Okay, and that's a legitimate answer. Think about it. You're given a poset and an element, and you cannot decide that. Yeah, that's
so A and B are in binary, right?
So yeah, everything here is in binary. So let me erase that because that's actually maybe not as revealing. And let me use the space to explain what's sort of going on. How can we possibly prove that? What does it really mean? Okay, what this really means is that Ramon in his proof is hiding something from you. Okay, I mean, Ramon in his statement of the theorem is hiding something from you. In fact, he's hiding the whole statement because it's long. And there is a small part of the statement where he basically says, look, equality cases, blah, 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 1, 2, 3. So somewhere in the very small print, he says, well, additionally, something has to be true for some polytoms. And so there are some numbers m equal to n. And then he says, look, this, I wrote it down. What did you say? So this condition should be viewed merely as a normalization. And that's such a tiny thing, non-normalization. We're all good with normalization, right? It's like scaling the convex body. Except that's where the whole thing goes. Checking that part is impossible. That's what I'm saying. So to understand this, so everything we're doing, actually, our paper doesn't use any of the Schoenfeld-Van Handen results. It's a completely independent paper, but we use it only in the sense that we need to know where to look for bad stuff. So in all these pictures, there's bad stuff happening, and bad stuff is happening here. This is where bad stuff is happening. So essentially, the way you should think about it is that, roughly speaking, they're saying that for some different poset, rho of P, for some different poset P prime, X prime, we have equality of those ratios. That's what they're saying. And that cannot be decided. You see what I mean? So what we're proving is that one can directly translate. I mean, we don't actually go do that, but one can directly translate this equality into that kind of equality in this tiny little special case. And that suffices for us to show that equality conditions of testing equality is actually not in the polynomial hierarchy. Because in this tiny little thing is not in the polynomial hierarchy. Is it clear? Because I want to maybe, since I do get a chance, I want to say a couple of words about part 4.
Igor, can you say a word about this? Where does the chain of reductions end?
Where does what?
The chain of reductions. You showed you reduce and reduce and reduce.
Yeah. So
which problem do you eventually end up with?
This one. I mean, okay. And then we need a complexity theoretic argument to show that this is not in pH, and that's a separate.
So where does this complexity theoretic argument hinge?
I think he's asking for the combinatorial problem.
So let me tell you sort of a slightly easier version of the combinatorial problem. So I suppose you're given 2 posets, and you're asking is well, number of linear extensions of P equal to number of linear extensions of Q. Can you do that? So both of these are Sharpe complete, but the proof of Sharpe completeness is, I mean, the proof of Sharpe completeness of number of linear extensions is not using parsimonious bijection. It's a completely different proof using Chinese remainder theorem. So you need so essentially we're saying that the results of this type, so one can show that this equality is in the polynomial hierarchy, even though we cannot actually show that this is NP-high. But we can still show that it's unlikely to be in NP.
Thank you.
Okay. So now what's really happening?
Here, if I may, I think Nadia asked what known result about the
no, known results. This is a known result. So
it is known, right?
As the end of no, this is known as a previous paper of myself.
Okay.
And we do need to show that number of linear extensions is Sharpe complete, and
but that's known.
That was known for
that was known, right?
That's from the 90. But
and
you need a complex theoretic argument to get to this.
To this from this, right?
Yeah,
okay.
This is not obvious.
Oh no, I'm not saying it is. Okay.
And I know. Give me 1 minute, and then you can just cut the questions. What's really happening is it's not true that I truly wanted to prove this result. What I wanted to understand is why the same question as Imo asked, why can't you prove standard inequality bijective? That's what I really wanted to know. And this answers my question. So I'll write one formula and then stop. So so this proves that there is no stability, but it will take me some time to formulate what I mean. But it does prove that, let me write it in shorthand. The square of n minus the product, that is not in sharp P unless pH collapses. So in particular, there's no combinatorial interpretation, the way we would think about it for the standard inequality. Now, if you had some kind of bijective proof, which shows how to inject, or injective proof, which shows how to inject this one into that one. Of course, you can do that by just ordering them lexicographically and just mapping them from one to another. But if you wanted that to be effective in any sense, that would give you that would give you a way to figure out what's not an image of the injection, and that would give a combinatorial interpretation. And we're saying that that's not true because that would contradict this theorem. Okay, so to be clear, this is for k greater or equal to 2, and k is, as you remember, the number of fixed elements Z in Z. So for k equal to 1 and for k equal to 0, this is no. This is SVH, and this is Svehong and myself based on the paper of mine Schenfeld. So so in those cases, the decision problem is in P, whether it's 0 or not. In this case, the decision problem, whether the difference is 0 or not, is not even in polynomial hierarchy. So it might still be that when k is equal to 0, this is still not in sharp P. I conjecture that. So for the most basic case of standard inequality, we don't know. But for the generalized standard inequality, we don't know. Thank you. Sorry for the delay.
We will leave the questions to private discussions. We will continue at 11:15.
You said it well.
Physically.